Hello, welcome back. This is Calculus by Dr. Oz. Today we're going over a brand new topic called the shell method, and it's an alternate technique to evaluate the volume of a solid of revolution. And we have two learning objectives to achieve today, and the first one is to find the volume of a solid of revolution using the shell method, obviously. And the second one is more like comparing the disk method and the shell method because one is more powerful than the other one for certain problems, certain exercises. So we're going to discuss about the differences between disk method and the shell method. All right, let's get started. All right, let me introduce you to the shell method quickly. So first off, the shell method is an alternate method for finding the volume of a solid of revolution, and the name comes from the fact that we're having cylindrical shells to approximate the actual volume of the solid of revolution. So what we do here is that we take a representative rectangle, and we have the axis of revolution here, as you see. And here is our rectangle, the red one. And what we do is we check the distance from the rectangle to the axis of revolution. Let's say from the center line, from the center of the rectangle to the axis of revolution, the distance is p here. Okay, so and then let's say like we have the length of the rectangle to be h and the width to be w. So essentially from the top part of the rectangle all the way to the axis of revolution, we have the distance p plus w over 2. And from the bottom portion of the rectangle all the way to the axis of revolution is p minus w over 2. All right, let's zoom everything back in, and we're trying to revolve this rectangle around the axis of revolution to get a cylindrical shell. And in the next slide, we're going to try to evaluate the volume of this representative shell here. So first off, what we have here is the outer radius of the cylinder and inner radius of the cylinder. So one is p plus w over 2, and the other one is the p minus w over 2. And we go ahead and calculate the volume of the outer cylinder and the volume of the hole, which is the inner cylinder. And when we subtract them, we get the volume of the shell. Okay, so the volume of the cylinder is pi times the outer radius squared times the height, and the hole, the volume of the hole is pi times the inner radius squared times the height. And if you simplify this out all the way, if you expand this quantity squared, if you expand this quantity squared, there's going to be terms all the way canceled, and then we get down to the formula of 2 pi p times h times w. So going back to here, 2 pi times the average radius, okay, so that's p, right? The average radius is just p from here to here. And then what else do we have? Height and thickness, right? Height is h and thickness is w. So essentially 2 pi times average radius is sort of like the circumference times the width and times the height is going to give us the volume of that shell, representative shell. All right, let's try this idea to revolve a region around an axis of a revolution. Let's say like we have a triangular region to consider, and we get a representative rectangle of thickness delta y, and let's say its length is h, okay, and this is its thickness, and the average radius, let's say, is equal to p of y, okay. And when you revolve this around the axis of revolution here, so you're going to get this kind of like shell. And in fact, it's just right here. And if you look at the three-dimensional object here, so that's exactly what you get. And by using the formula that we just derived, so the volume of the representative shell is 2 pi times the average radius, the height, which is in fact what I called as like length of the rectangle, times the thickness, which in case In this case, it's just delta y. So delta v is equal to 2 pi p of y, h of y, and delta y. And as you see that radius and height are written in terms of y. And remember that the whole idea in this chapter is to first evaluate the volume of the representative, let's say in this case it's shell, before it was a disk or washer, and then sort of like get the sum because we have a lot of rectangles within the region that we can come up with depending on our partition, and we get the sum of those and let that partition the length of the or the norm of the partition go to 0. In other words, we're increasing the number of rectangles within the region to be revolved around. So when you increase the number of rectangles, so the thickness delta y goes to 0 essentially. Like this thickness gets very small, and then we pass the limit. Okay, so that's exactly what we're going to do in the next slide. Okay, so we have a lot of representative rectangles, let's say, and when I say a lot, that means I originally take like n of them. Okay, so and this sum tells us a good approximation of the volume of the solid by using shells. Okay, so, and this is sort of like the formula that we have. What we're going to do here is just let n go to infinity. So we're going to increase the number of rectangles within that region. And here we go. As n goes to infinity, that means the length of the width of each rectangle is going to approach 0. In other words, the partition is going to approach 0. So the volume of the solid, so this sum, in other words, together with this limit, turns out to be an integration. So we talked about that earlier. And I told you like this process of passing the limit for the sum of the volumes is very important, and that's what we're doing here. And here, as you see that this limit of the sum as n approaches 0, or the norm of delta, the partition approaches 0, takes you all the way to this nice integral formula written in terms of y. Okay, so we have dy, so we have the y limits of the region, and as you see here, that the y values within the region are ranging in between c and d, so that's why this integral turned out to be an integral from c to d. All right, let's summarize this concept called the shell method, right? We have two different types of axes of revolution. One is the horizontal, the other one is the vertical. The representative example I just went through was for horizontal axis of revolution. As you see that I chose rectangles. In fact, the representative rectangle in this case parallel to the axis of revolution. And if you are talking about the vertical axis of revolution, that means you're going to choose again rectangles parallel to the axis of revolution. So here we have more like a vertical rectangle chosen from the region that is supposed to be revolved around. Okay, and here thickness becomes dx, and all of the quantities here, p and h, are written in terms of x, whereas in the other case, the horizontal axis of revolution, we had p and h written in terms of y. So essentially, if you would like to use the shell method, let's say for this case that the axis of revolution is sort of like parallel to the y-axis, so then the integral should be written in terms of x. And if you want to use the shell method with the horizontal axis of revolution, so the integral must be written in terms of dy, so the thickness is going to be exactly equal to dy. So this is sort of like the major difference between the shell method and the disk method. All right, let's practice this method on an example where you have a function x minus x cubed, and you have the x-axis, and you want to revolve the region bounded by x minus x cubed and the x-axis about the y-axis. So the axis of revolution is essentially y, okay? And if you graph the region let's say if you graph x minus x cubed together with x-axis, obviously this goes on and on, right? And then, but I'm interested in the portion of the x-axis stuck in between 0 and 1. So, so essentially we're talking about this region, and this region is going to be revolved around y-axis. All right, since the axis of revolution is y-axis, since I have the intention to use the shell method to find the volume, I'm going to choose a representative rectangle parallel to the y-axis. Here we go. So I have my representative rectangle, and if this is the case, remember that thickness is always delta x or dx. Okay, going back to this definition here, right? So we are in this case here. Hold on. We are in this case here. Okay, so the thickness is dx. So essentially, I'm going to write the radius and the height in terms of x. So that's going to be my next business. Okay, and the height of the rectangle is right here. Okay, and this is determined by obviously the curve, the function. And let's say like this p of x is x. Okay, let's say like your representative rectangle is x units far from the axis of revolution, so the corresponding height is going to be determined by this curve. In fact, the height is going to be the function x minus x cubed. Here, the labeling starts from p first. First, you determine the radius, and generally you call it x, at least for this case, so that the height is determined based on what the radius is, okay? And so now we have all the ingredients because P and H are all written in terms of X. So we go ahead and use the formula to come up with the volume, which is 2 pi times P of X times H of X times dx. And let's see what the limits of the integral are. Well, the x's within the region are ranging from 0 to 1, right? So this obviously tells us that a is going to be 0 and b equals 1. So we go ahead and plug that back in. Okay, so that we have 2 pi integral from 0 to 1, p is x, h is x minus x cubed dx, and the rest is just the evaluation of a definite integral. Okay, use the power rule of integration. Okay, and to do that, you first expand the whole thing out. So this is x squared minus x to the fourth. That's exactly what's written here, x squared minus x to the fourth. And now let's use the power rule for integration. It's minus x to the fifth divided by 5 plus x cubed over 3. And then let's plug in 1 for x. So 2 pi minus 1 over 5 plus 1 over 3 minus 2 pi, we plug in or substitute the lower limit in, but that is complete 0. Okay, and this takes us all the way to 4 pi over 15 for the volume of that three-dimensional object obtained by revolving the region around y-axis. All right, it's time for practice. Please visit the recitation PowerPoint slides where you're going to have 3 exercises back to back to apply the concept of the shell method. And for this particular case, we have a region bounded by the curve y equals x cubed, y equals 8, the horizontal line, and x equals 0, which is the y-axis. Okay, and we're going to revolve this region about y-axis. Okay, so you can go ahead and have your calculators ready to graph the region, or you can just hand sketch it. Okay, so the region looks like this, and we're going to revolve this region about y-axis. Remember that whenever we use the shell method, we use a representative rectangle parallel to the axis of revolution, and that's exactly what we have here. And if you revolve this around y-axis, so you're going to get a good cone-shaped graph. Okay, and you're going to try to calculate the volume of this three-dimensional object. Okay, and the second example is also about the use of the shell method, but this time we have the region bounded by the graphs of y equals 4x squared, y equals 4, that's a horizontal line, and x equals 0 is the y-axis. But this time we're going to revolve this region about the x-axis. Okay, so it's about like revolving this region about a horizontal axis. Okay, so the region looks like similar to what we had in the previous problem, but this time, since the axis of revolution is x-axis, so I'm going to take a representative rectangle parallel to the x-axis. So my rectangle is going to look like this. So the thickness is going to be here, obviously dy, different from the previous exercise. And you're going to start revolving this region around x-axis, and you're going to get this kind of like nice three-dimensional object. Okay, please practice this problem as well. And I think the final exercise in this list is, again, the application of the shell method, and I try explaining everything step by step within the videos. Please watch those videos. And then this time the region is bounded by a line, y equals 3 minus x, and y equals 0, which is x-axis. And we have x equals 6. We have a vertical line here, and we're going to revolve the region about x-axis. Okay, so you can go ahead and check what the region looks like first. And here is what we have. And we're going to revolve this region about x-axis, so that means I'm going to take a rectangle, representative rectangle, parallel to the axis of revolution, so that's going to come with thickness dy in this case. Okay, and you're going to revolve this region to get a good like cone-shaped picture here. All right, in this video, I introduced you the shell method. Depending on the horizontal or vertical axes of revolution, you have different formulas. Please practice the content that I just showed you in the recitation PowerPoint slides, and watch the videos. And I'll see you in the next video to talk about how we can compare the disc or washer method to the cylindrical shell method. All right, I'll see you there. Bye.